This is a second video on using fractional exponents in astronomy. If you haven't already seen it, you may find it helpful to watch a video on the luminosities of stars where I talked about some of the ideas that we'll use here. We're looking at the lifetimes of stars here, and in this case the lifetime of the stars refers to how long they happen to be consuming hydrogen in their cores. Stars are mostly hydrogen. They begin their lives as about 3/4 hydrogen and 1/4 helium, and for most of their lifetimes they're consuming hydrogen in the cores, actually turning it into helium. They consume the hydrogen through a process called nuclear fusion. If you want to learn about that, take astronomy. Since the other stages of a star's life are quite short compared to this stage, we think of this hydrogen fusing stage as the lifetime of the star. You may hear me refer to this as the main sequence lifetime. That's a term that we use in astronomy to refer to this stage of a star's lifetime. The lifetime of a star is going to equal how much fuel it has divided by the rate of fuel consumption. An analogy to this would be the lifetime of a bag of tortilla chips. In that case, what we would have is the number of chips in the bag divided by the rate of chip consumption. If you're the kind of person who can discipline yourself and manage to eat only 2 or 3 chips at a time, your tortilla chip bag is going to last a long time. But if you're like me, and as soon as that bag is opened, you just start chowing down, your bag of tortilla chips isn't going to last very long. Same thing with stars. They start off with a particular amount of fuel. They have their rate of fuel consumption, and the more rapidly they consume the fuel, the shorter their lifetime will be. Well, here's what it relates to in terms of things we can measure. The amount of fuel is actually the amount of mass that the star happens to have. The rate of fuel consumption is the rate at which they convert mass into other forms, and in this case it happens to equal their luminosity. In the previous lecture we actually looked at a relation between these two things. The mass I'm just going to abbreviate with a capital M. In the previous lecture we found out that the luminosity is proportional to the mass to the 3.5 power. We have a relation here where the lifetime, which is going to equal the mass divided by the mass to the 3.5 power. Well, you probably know that when you divide things with exponents, you subtract the exponents. That mass on top is effectively a mass to the 1. Down here we've got a mass to the 3.5, and you subtract the exponents, you'd get the mass to the minus 2.5 power, or we could also write that as the lifetime is equal to 1 over the mass to the 2.5 power. This is an interesting relationship. What it means is that the more massive the star, the shorter its lifetime will be. Our example here, if a star is 16 times as massive as the Sun, how does its lifetime compare? In this case, as in the previous video, we're going to always be comparing things to the Sun, and so we'll get numbers compared to the lifetime of the Sun. And at the end of this video I'll talk a little bit about those actual numbers. So let's see how this works. It would be the lifetime would equal 1 over, in this case we'll have a 16 down here, to the 2.5 power. Now we'll convert that 2.5 into a fraction so we can actually evaluate this. Doing it in our head, I'm going to pick numbers so we can always do that. We'll have 1 over 16. 2.5 is 5 halves, and from this point on I'll probably just write that as 5 halves. This will equal I'm going to split that 5 halves into a 1/2 and a 5. So I'll have a 16 down here to the 1/2 to the 5th. When we raise a power to the power, we multiply the exponents, and 1/2 times 5 would give me that 5 halves. 16 to the 1/2, that's the square root of 16. That's just 4. So I'd have 1/4 to the 5th. I'd end up with a lifetime of about 1/1024th that of the sun. We're not going for that much precision here. I would just round that. These squiggly equal signs means about equal to. I just call it about 1/1000. And what that means is a star that is 16 times as massive as the sun will have a lifetime that is only 1/1000th the lifetime of our sun. So a much shorter period of life. And it happens because of that much greater rate of fuel use. It has 16 times as much fuel to begin with, but it burns it at such a greater rate that it doesn't last as long. Let's look at another example. If a star is 49 times as massive as the sun, how long is its lifetime compared to the sun's? We'll do it the same way. The lifetime will equal 1/49, and I'm just going to write it as 5 halves this time, and go through the same thing I did before. 1/49 to the 1/2 raised to the 5th power. 49 to the 1/2 is the square root of 49. It'll end up being 1/7 to the 5th, a number I have to do on my calculator. When I do that on my calculator, I get 16,807, which I would just round to 1/17,000. And it's a much shorter lifetime. When it was 16 times as massive as the sun, it lasted 1/1000th as long. If it's 49 times as massive, it's 1/17,000th as long will be its lifetime. So amazing things happen. Let's look at one that's less massive than the sun. I said earlier that the general rule was that the more massive the star, the shorter its lifetime. Let's look at what happens when it has less mass. If a star is 1/4 the mass of the sun, how long is its lifetime compared to the sun's? We'll do this the same way. The lifetime will equal 1/the mass to the 2.5 power. This time the mass is 1/4, and again that's compared to the sun. 1/4 to the 2.5 power, 1/1/4 to the 5 halves. That's 1/1/4 to the 1/2 to the 5th power. We've been doing this trick all along here. 1/4 to the 1/2, that's like the square root of 1/4. That ends up being 1/2. 1/2 to the 5th power. The lifetime of that star, 1/2 to the 5th, ends up being 1/32. So 1/132nd, which is actually 32. Turns out a star that has 1/4 the mass of the sun will have a lifetime that's about 32 times as long as that of the sun. So a less massive star lasts a lot longer. The sun's lifetime will actually be about 12 billion years. That's a long time. It's about halfway through that, or a little bit less than halfway through that right now. So this star that's 1/4 as massive, with 32 times that lifetime, you'd multiply 32 times 12 billion years, and you'd get a much longer lifetime for a star that's only 1/4 as massive. Turns out those smaller stars, 1/4 the mass of the sun or less, are actually the most common type, and they're going to be around for a long time.